Hi, my name is Gabriel Bernal. I am Chief Science Officer at INGENIAR Risk Intelligence and Technical Coordinator for the development of the GIRI model. GIRI is both a catastrophe risk model for the infrastructure of the world and a resilience index. Furthermore, GIRI is the only index to implement a holistic approach to infrastructure disaster resilience, making it versatile and powerful in the communication of current states of risk and resilience, and the required actions to improve resilience and reduce risk. Unlike what is commonly believed, resilience is originally a concept from the mechanics of materials. Let us think of this steel bar subjected to tensile forces. As the force increases, the bar will elongate as a result of its elasticity, which can be recorded in a stress-strain diagram such as this one. The increase in tensile stresses causes deformation in the material that is proportional to those stresses. That is, there is a linear relationship within the elastic range of the material between stress and strain. At this point, the material has accumulated an amount of elastic energy equivalent to the area under the stress-strain curve. Since the material is within the elastic range, it has the capacity to return to its original state once the stress is removed. Resilience, therefore, is the ability of a material to absorb and store energy when it is elastically deformed, releasing it upon removal of the load without undergoing permanent deformation. With the original definition in mind, let us now consider the resilience of infrastructure systems. Measuring infrastructure resilience to natural hazard events is not an easy task. It may be accomplished through two main approaches. In the first approach, resilience is quantified through attributes or properties of the infrastructure systems that are known to be related or beneficial to resilience. For example, attributes like robustness, resourcefulness, adaptivity, recoverability, among others. The application of these type of methods requires a definition of a system of indicators that reflects the attributes and the extent they are present in an infrastructure system. In the second approach, a performance curve serves as the main metric of resilience, informing on the ability of a system to absorb impact from an external disturbance and to respond and restore performance in an efficient and timely manner. In the pre-event state, the system functions as expected, having a predefined performance level that responds to demand and offer conditions. Once a disturbance occurs, like this earthquake for example, the performance drops abruptly to a remnant amount that depends mainly on the system capacity to absorb. Physical vulnerability strongly modulates this capacity. After the event, the degraded system needs intervention to be able to perform, at least, as in the pre-event state. The effective recovery of the system usually takes some time to begin, depending on the capacity to respond, which is strongly related to operational issues. Preparedness usually plays a key role in the response time. Then, the recovery of performance begins as fast as the system's capacity to restore the lost or damaged elements, facilities, or networks. Both approaches have their benefits and limitations, but when jointly considered, they have the potential to inform infrastructure stakeholders with a more complete understanding of infrastructure resilience. The Global Disaster Resilience Index, or GIRI, is designed as a combined approach to assess infrastructure disaster resilience. The performance curve, originally proposed by Michel Bruno in 2003, is sufficiently general to represent the performance of any type of infrastructure system, such as electric power, water and sanitation, transportation, hospital infrastructure, and even residential infrastructure, among others. The performance measures the capacity of the system under study to provide the service for which it was built. Appropriate performance implies that the system operates under adequate conditions relative to the demand placed on the service it delivers. This means that performance curves are the most general model for measuring impacts on elements of the built environment. In probabilistic risk modeling, it is common to describe damage in infrastructure elements through fragility curves. These make it possible to associate a probability with different damage states of an element as a function of hazard intensity. An additional level of complexity is reached when characterizing the exposed elements through vulnerability functions, which provide information not about damage itself, but about economic loss relative to a replacement value estimated for the exposed elements. Catastrophe risk models usually quantify risk in terms of direct loss. However, performance curves encompass a broader meaning, as they involve information related to both damage and loss, which are reflected in the drop in the performance following the occurrence of a disturbance, as well as in the operational and governance conditions of the system that provide it with the capacity to respond to the event and restore what has been lost. The area above the performance curve is an indicator of the system's set of capacities, and therefore of how easily it returns to the expected level of performance. This area is thus a resilience metric. In fact, it reflects the lack of resilience of the system. Therefore, a system with greater capacities to absorb, respond, or recover exhibits a smaller area above the performance curve. In this way, it becomes possible to measure the resilience of infrastructure systems with different capacities, as well as the potential benefit of implementing risk management actions to enhance the resilience of those systems. To quantify the GIRI, first we simplify the shape of the performance curve, as shown. The three capacities, to absorb, to respond, and to restore, as well as the two variables in the curve, performance and time, are normalized and transformed into indicators. Then we take advantage of the relation between the resilience capacities and attributes, defining the one-to-many relationships illustrated. These attributes are accounted for through a system of indicators carefully selected to reflect on the corresponding attributes that are used to quantify the corresponding capacity indices, making it possible to approach a measurement for resilience from a set of indicators available for most countries and territories in the world that are transformed into commensurable variables through the use of membership functions, and then weighed and added to make the index of each capacity. GIRI is calculated as the complement of a normalized relation between the area and the perimeter of the shape of this simplified and attribute-based performance curve. Now, the only remaining element to assess is the disturbance, that has an effect on the size of the drop from the pre-event state. This disturbance is unspecific, meaning that it is impossible to know its size, characteristics, and origin beforehand. Or, in other words, it may come from any hazard at any moment. We define this disturbance as a random loss of random occurrence. This implies that the disturbance must be quantified through probabilistic risk assessment using a CAT risk model. The CAT risk modeling approach used for GIRI is depicted in this slide. It has three components: hazard, interpreted as a set of events that are mutually exclusive and collectively exhaustive, covering all the possibilities in which hazard may manifest in a territory. Hydrometeorological hazards are modified by climate change. The exposure, which is the collection of elements and components of the infrastructure systems, and the replacement value, and the vulnerability, which relates hazard intensity to cost of damage for each individual element. Their appropriate combination using a CAT risk modeling framework returns financial metrics such as the average annual loss, the PML curve, but more importantly, the loss exceedance curve, that speaks about the probability distribution of the loss in the infrastructure of a country, going from low loss events of high probability to high loss events of low probability. The loss exceedance curve speaks about the rate, that is a measure of frequency, probability, or likelihood of loss amounts, being loss itself a measure of impact, of the size of the consequences. This curve covers the full spectrum of events affecting the infrastructure of a country. Very common events with relatively lower losses, like landslides or floods, are more relevant to the first portion of the curve. Intermediate impact events of lower probability, like droughts or tropical cyclones, are represented in the central portion of the curve, while high impact events of very low probability, like tsunami or earthquakes, influence the curve in the last portion. The way the events occur in time and the impact caused, like in this example for different hazards, holds the rate and loss relationship expressed by the loss exceedance curve. The realization shown may even be different, because this metric is not a predictive tool, which implies that within the loss exceedance curve exist all the possibilities or combinations of event occurrence and consequences to the infrastructure. In other words, the loss exceedance curve fully represents a random loss of random occurrence, which is precisely what is needed for GIRI. Other relevant metrics can be extracted from the loss exceedance curve. For example, if we aggregate the losses over time, the average rate of increment of the accumulated loss is the average annual loss. That is a very important and robust metric of risk. In a nutshell, the average annual loss represents the amount that needs to be paid annually to cover, in the long term, all the losses derived from the occurrence of natural hazard events affecting the infrastructure of a country. In actuarial terms, it is very similar to the pure risk premium of an insurance instrument. Other important metric comes from measuring the average time of occurrence of events that exceed different amounts of loss. The probable maximum loss is an important risk metric that best relates to the real expected loss when a disaster occurs. In contrast to the average annual loss, the PML is not a flow variable, but a feasible amount of loss that may occur at some unknown moment in time. Besides the GIRI itself, we have developed two other disaster resilience metrics that complement the assessment. The resilience risk plot, that shows how resilience, measured as the GIRI, changes with the amount of risk, is an important metric that summarizes the effect that reducing, but also increasing disaster risk has on the country's overall resilience. The shape of the curve changes among countries to reflect the influence of resilience capacities. Finally, we found that the derivative of the resilience risk plot is the performance curve, more precisely the shape of the performance curve. This shape is very important to inform on the current level of resilience, but also to design risk management and adaptation plans to achieve a resilience target. GIRI is quantified for all countries in the world. It covers risk and resilience assessment to multiple hazards, including earthquake, tsunami, landslide, flood, tropical cyclone, heat waves, and cold waves. The last five with models that explicitly incorporate climate change through the definition of upper and lower bounds of climate variation, in accordance with the most recent IPCC future projections. The infrastructure sectors included are power, highways and railways, transportation, water, wastewater and irrigation, communications, oil and gas, and buildings. Each sector is represented in the model through the full collection of assets and elements, country by country, with novel pricing and physical vulnerability models. All hazard models are global, covering the whole planet, and event-based, built up by many individual events that, in conjunction, define all the ways each hazard may manifest in the territory. Nonetheless, it is simpler to show these integrated uniform hazard maps for illustration. The total economic value of the infrastructure of each country, illustrated here as bags of money, is approximated as a fraction of the produced capital within the total country wealth. It is important to approximate this amount to then distribute it over the individual components of all sectors and subsectors of infrastructure that have unique characteristics and geographical locations. This approach allowed us to exploit the most of all available geospatial data of infrastructure while constraining it to the macroeconomic capital stock for each country. GIRI incorporates state-of-the-art models of vulnerability based on archetypes of infrastructure components. The archetypes are general models of how the elements of an infrastructure system are typically made up of a set of components. Infrastructure elements like thermal power plants, airports, refineries, or wastewater treatment plants, for example, are made of individual constructions, machinery, and equipment that will suffer damage very differently when a hazard event strikes, contributing to the overall vulnerability of the archetype. Here are some examples of vulnerability functions for thermal power plants and different hazards.
Furthermore, GIRI incorporates state-of-the-art vulnerability models for duration-sensitive events, such as heat waves and cold waves. These are implemented through vulnerability functions indexed to bidimensional intensity measures, thereby capturing the complexity inherent in both the manifestation of the event and the duration of extreme conditions.
With over 50 different archetypes defined for this assignment, the GIRI library of vulnerability functions is, at present, the most complete resource on vulnerability models for CAD risk assessment of infrastructure systems.
All risk models are created using Capra Robot, which is INGENIAR's disaster risk assessment engine and probably the most complete CAD risk modeling suite available nowadays, in terms of its coverage of perils and exposure sectors. Capra Robot incorporates state-of-the-art physics-based models for multiple perils. On the geological side, these include earthquakes, tsunamis, and volcanic eruptions. On the hydrometeorological side, they encompass droughts, floods, wildfires, pandemics, cold waves, heat waves, tropical cyclones, convective storms, and landslides, all of which modeled through the implementation of a stochastic weather generation framework, within which climate change projections can be integrated and downscaled into meteorological forcing variables. Capra Robot covers risk models for a wide variety of sectors and perils beyond the current scope of the GIRI model. However, this provides GIRI with an unprecedented potential for scope expansion, through Capra Robot's capability to express risk from any combination of peril and sector in terms of probabilistic CAD risk metrics and performance curves. The amount of results included so far in GIRI is huge. We are covering 8 sectors, subdivided in a total of 26 subsectors, and 7 hazards, some of which have variations due to climate change. The overall matrix of possibilities is very large. However, not all cells in this matrix are included in the model. For earthquakes, tsunami, tropical cyclones, floods, heat waves, and cold waves, including the effect of climate change, all the combinations are covered, as shown by the squares in each cell. For landslides, both earthquake and rain-triggered, the assessment is only performed on the roads and railway tracks of the world, where it makes more sense. The match between landslides and other infrastructure sectors is not as well represented in this model due to scale constraints. Green and blue squares indicate results from the first and second iterations of GIRI, respectively. Inside each cell, we will find a full set of risk and resilience metrics, including the loss exceedance curve, the PML curve, the average annual loss, and the GIRI, with the disaggregation of all the indicators that make up the resilience capacities. Each cell is a vast source of information on disaster risk and resilience for a sector and hazard combination. What is illustrated here is the set of results for one country, meaning that similar results are calculated for all countries in the world. At present, there is no other catastrophe risk modeling effort as prolific, versatile, and robust as the model for GIRI. With such an amount of fit-for-purpose metrics, the full spectrum of applications of GIRI is still being discovered. For example, some uses of these results include a risk profile by country, very helpful for governments to understand their fiscal risk for all infrastructure sectors and be able to inform and develop national resilience policies or strategies. GIRI provides a holistic view for the risk profile, with a solid foundation in probabilistic CAT risk metrics, but transcending their actuarial and financial nature into a metric of infrastructure resilience and its individual capacities, useful for governments to diversify investment in risk management and climate change adaptation, referring to construction, operation, maintenance, and repair among gray, green, and blue infrastructure, but also investments on the social, environmental, and economical transformations required to increase resilience. The GIRI risk model is versatile enough to allow for the verification of pertinence and effectiveness of risk management and climate change adaptation actions and plans. Using risk control engineering, it is possible to fine-tune a collection of risk management and climate change adaptation actions to achieve a target resilience level. Actions like design, construction, and land use standards, response, recovery, and adaptation protocols, financial risk transfer schemes like insurance, CAT bonds, issue of contingent debt, among others, or interventions oriented by resilience attributes and principles. With such tools, governments can have an evidence base for the development of resilience standards in each sector. This is, in other words, to evaluate the effectiveness of different risk reduction measures to make decisions about the optimal level of resilience.
GIRI currently incorporates infrastructure projecting, focused on the projection of future infrastructure growth, investment requirements, and disaster risk evolution. It integrates demographic trends, infrastructure patterns, and vulnerability assumptions to estimate how infrastructure exposure and associated losses may change under different development pathways, including business as usual conditions, resilience oriented trajectories, and scenarios consistent with achieving the Sustainable Development Goals by 2030. Therefore, GIRI delivers metrics for all projected cases, making a strong case for resilience-oriented development of infrastructure as an effective strategy for risk reduction. Furthermore, GIRI has already implemented downscaled models for some territories, where infrastructure risk is modeled at the highest possible resolution. So far, the GIRI downscaled models include Chile, Fiji, Nepal, Mauritius, and 4 Indian states, where risk metrics are obtained even at a building-by-building resolution.
GIRI is a cross-cutting model and index that provides robust results and metrics, useful to inform, design, and monitor public policy in all aspects of development. It takes into consideration disaster and climate risk as a byproduct of the existence of exposure and vulnerability conditions in the infrastructure systems, over territories in which the occurrence of hazard events is natural. Climate change is explicitly incorporated in GIRI, modifying the conditions of occurrence of natural hazards and the risk landscape, but in a way that is deeply uncertain. This justifies the use of probabilistic approaches to account for risk and resilience. Due to its probabilistic and holistic nature, GIRI highlights the physical and intangible risk and vulnerability drivers, thus enabling the identification of corrective and prospective interventions to be done. Furthermore, the architecture of GIRI allows it to incorporate risk management and adaptation actions within the model, providing robust evidence and data on effectiveness for decision making. And this is the same architecture that allows GIRI to evolve and expand. GIRI can support risk quantifications for other sectors and systems not included in this iteration, such as agriculture and ecosystems, which can be understood nowadays as critical infrastructure.
Measuring is essential for decision making. What is not quantified cannot be managed. Risk assessment is crucial for revealing and understanding risk and for holding decision makers accountable. Disaster risk represents a contingent liability and thus a sovereign risk for society. Risk reduction, prevention, and resilience-based design are duties in risk governance and the nation's accountability. Tracking DRM progress over time requires evaluating the trade-offs involved in development transformations. Building resilience is building a future, strong, adaptive, and full of potential. Resilience-based, it's protection with returns. Understanding probable losses from potential hazard events provides a strong incentive for countries to develop planning strategies and tools to manage risk. This includes allocating sustained budgetary resources needed to reduce potential damage, enhance resilience, and safeguard development through transformative actions. It is possible to demonstrate how probabilistic and holistic risk models can be integrated into a methodology that truly leverages the benefits of aggregating and disaggregating both hard and soft risk drivers. This integration helps identify the necessary corrective and prospective interventions. Focusing on the future and improving forecasting capabilities enhances the ability to take effective action in the present. This is the Global Infrastructure Risk Model and Resilience Index. Thank you. And remember, if you're not profiting from resilience, you're already paying for vulnerability.